Good morning, ladies and gentlemen. I'm very pleased to welcome all of you at the ceremony of the inauguration of 2020-2021 academic year at the International Environmental Doctoral School associated with the Centrum for Polar Studies at the University of Silesia. During the epidemic, most daily activities, including academic life, have to be moved to virtual space. This also applies to our today's ceremony, which takes place remotely and broadcast live on YouTube. I'm convinced that, especially now, building a bond and a sense of community should be our responsibility. To be with us more personally, I would like to kindly ask newly admitted doctoral students as the main actors of today's ceremony to turn your camera on. Okay, thank you. Today's ceremony has been honored by the presence of distinguished guests. I'm very pleased to welcome His Magnificence Rector of the University of Silesia in Katowice, Professor Ryszard Koziołek.
Hello, good morning to everyone.
The inauguration is also honored by His Magnificence Vice Rector for Staff Development at the University of Silesia, Professor Ewa Jarosz.
Good morning, nice to meet you.
I'm very pleased that invitation to inaugural ceremony has been accepted by Professor Jan Pawłowski from the Department of Genetics and Evolution, University of Geneva and Institute of Oceanology, Polish Academy of Sciences. Professor Pawłowski will deliver us inaugural lecture. Professor is dealing with some technical problem, however, I believe he will join us soon. Finally, I'd like to warmly welcome the main actors of today's ceremony, the PhD students of the International Environmental Doctoral School. I'm also very pleased to welcome all participants of this ceremony who watch us live on YouTube, especially directors of partner institutes of the Polish Academy of Sciences and co-host of this ceremony, Professor Beata Orlecka-Sikora, the director of the Institute of Geophysics, Polish Academy of Sciences, Professor Łukasz Stetner, the director of the Institute of Mathematics, Polish Academy of Sciences, and Professor Jan Marcin Węsławski, the director of the Institute of Oceanology, Polish Academy of Sciences. I'm also very pleased to welcome representatives of authorities of the University of Silesia in Katowice and institutes of the Polish Academy of Sciences, the head of the Center for Polar Studies at the University of Silesia in Katowice, Professor Jacek Jania, members of the board of the International Environmental Doctoral School and International Advisory Board, members of Splendid Senate of the University of Silesia, deans and directors of institutes, representatives of the academic community of the University of Silesia, and associated with International Environmental Doctoral School, Maria Curie-Skłodowska University, supervisors, lecturers, PhD candidates, students, administrative staff, and all distinguished guests. I'm very pleased that you are with us. And now I would like to kindly ask His Magnificence Rector of the University of Silesia in Katowice, Professor Ryszard Koziołek, to open the academic year at the International Environmental Doctoral School associated with the Center for Polar Studies at the University of Silesia in Katowice, and to address us welcome words.
Thank you very much. Thank you, Mr. Dean. I'm coming. Okay. Ms. Rector, Mr. Dean, all distinguished guests, ladies and gentlemen, dear PhD students, let me express this formula. I solemnly announce I hereby open the academic year 2020-2021 in the International Environmental Doctoral School associated with the Centrum for Polar Studies at the University of Silesia in Katowice. Quod felix faustum fortunatum sit. May it be happy, favorable, and prosperous. We did it. Dear PhD students, I'm very glad that you chose the International Environmental Doctoral School as your place of research. It's an excellent school, outstanding scientists, and a unique educational program. I'm sure that you are just starting your great scientific adventure. Learning and science require faith and hope, not only hard work. Science is a matter of faith because we believe it will solve the most important problems facing mankind today and in the future. People benefit from science every day, yet they don't believe the diagnosis of scientists. They don't believe in vaccine effectiveness or the climate crisis. People prefer to live within the circle of their imaginations. Man would like to exploit the planet and take natural goods to these countries, homes, and families. They believe that they live in the circle, in a closed sphere. The German philosopher Johann Herder compared such an ideal homeland to a sphere in which one tribe lives that speaks one language, separated from others, like in Tolkien Lord of the Rings. The Western world is the Shire, the rest are Mordor. The man in the sphere lives huddled in the cramped space of his every diminishing small territory, hidden in fear of the ever larger and larger world outside. Science tells us that the world is one, that the Shire and Mordor are the work of the same human hands. They are the hands of the man who builds and destroys. I'm the historian of literature, so let me quote a piece from the literature. Victor Hugo, in his novel Sea Workers, calls our species Homo edax. Homo edax in Latin, in English, it means the destructive man. Hugo claims, however, that man is a much more effective destroyer than time or the elements. We know it well. We are at the point no return. There is no shelter in any sphere. We are on the surface of the sphere. It's the earth we share with all beings. Applied sciences have devastated our planet a lot. Paradoxically, only science can save us. Will he make it in time? Will you, young scholars, will you save us? Another writer, Franz Kafka, wrote a strange mystical sentence. There is infinite hope, only not for us. Another, again, there is infinite hope, only not for us. Let us give up mysticism. Let us see in this sentence the prophecy about climate change. In my interpretation, hope means a change in climate policy, the struggle against global carbon emission and keep the planet from melting down. But Kafka said that this kind of hope is not for us. Scientists have warned us for the last 30 years, and despite the earnest efforts, we have made essentially no progress toward reaching the goal. Today, the scientific evidence verges on irrefutable. If you are younger than 60, it's my example, you have a good chance of witnessing the radical destabilization of life on Earth. Massive crop failures, apocalyptic fires, imploding economies, epic flooding, hundreds of millions of refugees fleeing regions made uninhabitable by extreme heat or permanent drought. If you are under 30, that's yours example, you are all but guaranteed to witness it. Science says it today. And yet I believe that new science will turn out not to be true. The project like the International Environmental Doctoral School offers me the hope that the future, while probably worse than the present, might also in any kind be better. All of you, young scholars who are starting the new academic year, you give me hope for today. Good luck in the fight for our future. And don't worry about the epidemic anymore. It will pass through science. Thank you very much. Have an exciting time.
Thank you very much, Professor Koziołek, for inspiring speech. I believe that the words will become true in ongoing academic year. Then I would like to ask Professor Ewa Jarosz, Vice Rector for Staff Development at the University of Silesia, to give us an inaugural speech.
Okay, so again, good morning. I'm very pleased to be here. And His Magnificence, dear Dean, dear guests, and primarily dear PhD scholars, I'm very pleased to welcome you too as His Magnificence at the University of Silesia. We are happy that you chose doctoral school at our university as a location for your scientific development and as a place where you are going to realize and nurture your scientific passion. University is an institution that was growing up through centuries with the concept of autonomy, freedom of research, and the peer review as the measure of the quality of published research. These values cut across national boundaries and cultural differences. These values we are trying to nurture at the University of Silesia, sometimes doing it against external conditions. The university must generate excellent research, must produce and disseminate knowledge at the highest scientific level. This purpose requires a selection of the best candidates for research. This process can be seen as funnel-shaped. At the beginning, candidates for the PhD come pouring in, but the funnel narrows quickly, so many are rejected, and only a few get through to a further academic career. So you, doctoral students, may be proud. You have been chosen as the best candidates. Congratulations. You may be proud, but also you have to be aware that together with becoming a member of the university research community, you take the responsibility of not only your own scientific development, but also of building the knowledge, of doing research at the highest possible level. And you are expected to cultivate our values: reliability, honesty, autonomy, and independency of research. Usually we say something more to our PhD students for the beginning of the study. I'm not good at polar and ocean issues, icebergs, glaciers, whales, polar bears, and water. So today, I'm going to give some attention to emotions of research and to passion as love of the science and research. Emotions and science. You're wondering why I'm linking them. University is commonly seen as kingdom of the mind, not the space for emotions. Charlotte Bloch, the Dutch researcher, writes these words in her book titled Passion and Paranoia, Emotions and the Culture of Emotions in Academia. The university word is generally associated with rationality, with methodological principles, objectivity, and logic argument. From this point of view, emotions appear to be alien, irrelevant, and disruptive. However, this does not mean that academia does not have a culture of emotions. Indeed, university life embraces many strong emotions. According to Charlotte Bloch, academia and research activity itself is a setting for all kinds of emotions, including joy, fun, humor, laughter, but also frustration, disappointment, envy, mistrust, and malice. Different studies on emotions of research show a wide range of feelings, from uncertainty, curiosity, or even despair, till unhealthy obsession or unreasonable, insistent stubbornness. What I want to emphasize is that research is an activity that involves the whole person. Research involves our minds, but also our emotional spirit. Research springs from passion and emotions and entails passion and emotions. Passion is the basis to researchers' motivation, inspiration, and engagement to build the knowledge. Passion gives energy to research, and research gives a sense of freedom and sense of authenticity. Research is indeed based on belief, trust, and hope. Hope to make a discovery, to touch the substance, to disclose the truth, or sometimes many different truths. But research activity is intoxicating in itself, and just like giving us a sense of delight and involvement, and is seducing us with experiencing challenges or dealing with something not yet known, with the feeling of a creation and the ecstasy of discovery. This applies to all researchers, but is perhaps especially pronounced at the PhD level. Your life is going to be focused upon research. You will be experiencing passion and many emotions. And lucky you are. Luckily, your time during your PhD study is devoted for this. Other researchers really envy you this possibility. Frankly, I do. So, as persons stepping in the world of research, as newcomers in the university research community, be sensitive to your passion and your emotions. Be mindful of their role and their meaning in research, in creating discoveries, in building the knowledge, and building you as individuals. Appreciate these emotions, even if they are racking or too intense. So good luck in your research, in your studying, but also in meetings with your research emotions. Thank you very much.
Thank you, Professor Jarosz, for words addressed to the community of the International Environmental Doctoral School. Before I give the floor to our PhD students, I would like to say a few words. His Magnificence, dear PhD students, distinguished guests. Last year was the first academic year of the International Environmental Doctoral School. It fell in a difficult period of struggling with epidemic and its social consequences. For doctoral school, it was a great challenge how to manage the in the conditions of limited academic mobility, field works and laboratory research, and it required both organizational changes in education and research. I was impressed with the creativity shown by lecturers and quickly adapt the form and content of courses to the online education. At the same time, I'm extremely proud of the achievements of PhD students in the last year of their last year of education at doctoral school. Several papers of doctoral students have been published in reputable scientific journals, which proves the advancement of the work of young researchers. Our PhD students have been also active in applying for research grants. Most of the applications were successful. They get funding from Preludium 18 program, the Arctic Field Grant in collaboration with the University of Oslo, funded by Research Council of Norway. In addition, PhD students successfully applied for funds for remote sensing data acquisition during SciOS Airborne Remote Sensing 2020 campaign. Last academic year, PhD students were authors or co-authors of oral presentations and posters on international scientific conferences, including Svalbard Science Conference, IASC Network on Active Glaciology workshop on dynamics and mass budgets of Arctic glaciers, SciOS online conference on Earth observation, remote sensing, and geoinformation in Svalbard. PhD students completed traineeship in international research centers, Centro de Estudios Científicos in Chile, and Svalbard Integrated Arctic Earth Observing System, SciOS, in Svalbard. Despite the restrictions caused by pandemic, some of PhD students took part in field campaigns, including scientific expedition to Spitsbergen, as well as AREX and comeback research cruises. I wish this year will be even more abundant in scientific achievements that will lead you step by step towards completing your doctoral projects. I hope you will be an inspiration for PhD students who are just starting their education in the doctoral school, to whom I would like to turn right now. Dear newly admitted doctoral students, you've been selected from over 70 candidates. That means you have to be talented and forward-looking young scientists. I would like to congratulate you on selecting the International Environmental Doctoral School. It's really a great place to make your dreams of scientific career come true. You will work in interdisciplinary network of the most reputable units of the Polish Academy of Sciences and one of the most dynamic Polish universities, the University of Silesia in Katowice. Our doctoral school is not focused on a large number of students, but on selected young experts. Our ambition is an individual approach and creating comfortable conditions for our doctoral students for personal and scientific development. The International Environmental Doctoral School offers interdisciplinary and international education. We would like to show how doctoral projects can benefit from other scientific disciplines. That will allow you to see fascinating knowledge located in niches and the boundaries of the disciplines. I'm convinced that our courses conducted by recognized Polish and foreign lecturers will help you to achieve this interdisciplinarity. As you can see, you belong to a young international community, and I believe that you will exchange different experiences and richness of your cultures. I wish you a successful academic year and great scientific discoveries. And now I would like to ask newly admitted doctoral students to present themselves and the subject of doctoral projects. As a first one, I would like to ask Katarzyna Stachniak. Please introduce yourself.
Good morning, everyone. My name is Katarzyna Stachniak, like you say. And from today, I already officially said that I have started my doctoral studies. I cooperate with the University of Silesia in Katowice. I have continued my passion for science since my bachelor studies, geography, when I first had the opportunity to do fieldwork, my first research in Svalbard. And the next, during my master studies, I really wanted to get more experience in scientist's life and study in Svalbard. I had an opportunity to take a course at University of Svalbard about permafrost and perglacial environment in Longyearbyen. And after that, I moved to Hornsund, which I loved, where I spent more than 2 months in small Wrocław station to monitor the ablation season in the glaciarized basin. And I knew already that the Arctic hydrology is my passion. And on the basis of this work, I completed the subject of my master thesis. It was about hydrological and hydrogeological processes in the foreland of the Verenchelbrien glacier. And it was focused on groundwater flow modeling, groundwater runoff and retention possibilities in the active layer sediments. It was focused on marginal zone of the glacier without the whole body of glacier. And exactly 2 days after my graduation, I started working as a technical meteorologist as a part of 31st Polish Polar Expedition in Hornsund, where I spent 13 months overwintering. So when I come back, full of new experiences, I still knew that I was positively dependent on scientific work. So now, as a part of my doctoral thesis, I will be working on the subject of evolution of drainage system in glaciarized Arctic basin, driven by climate changes at Verenchelbrien catchment, of course, Svalbard. My PhD supervisor is Professor Jacek Jania. And the main purpose of this thesis, of this project, is to determine the impact of climate warming on the drainage system. This is the Portema Glacier, and it's for field and water budget using observation and modeling data. The main point is to indicate the leading factors and evaluate trends of changes in water circulation affected by climate warming. Of course, in 3 steps. First, the contemporary state of drainage system. Second step for handcasting using archival data. And the third step, prediction under different scenarios of climate changes. And additionally, during this work, I will check the assessment of capabilities and limitations of the numerical modeling, various tools in glaciarized basin. So this is my main interest. And this is all about me. So thank you for the attention.
Thank you, Katarzyna. Then Kayode Adebesin, please, it's your turn. Okay, I guess that Kayode has some technical problems, so let's move to the next one. It's time to give the floor to Veronica Patoa.
Good morning, everyone. My name is Veronica Patoa, and it's really a pleasure for me to be here with you all today. I am master graduate of oceanography at the University of Gdańsk, and my master thesis was about the mesoscale variability of zooplankton in Isfjorden, an Arctic fjord. I specialize in marine biology and mainly in zooplankton of polar marine ecosystems. I also have the opportunity on my master's studies to be a part of the cruise RX, which is annually expedition of Institute of Oceanology, Polish Academy of Sciences in 2017. And for several years, I also cooperate and work with the scientists from the ecology department of this institute. And here I got into the first year of the International Environmental Doctoral School for a PhD project about the seasonal and interannual variability of meroplankton in Isfjorden, an Arctic fjord. And my supervisors are Professor Piotr Kukliński and Dr. Marta Ronowicz from Institute of Oceanology, Polish Academy of Sciences in Sopot, and Professor Agata Weidman-Zwolicka from Institute of Oceanography at the University of Gdańsk. Back to the topic, the meroplankton is of course the part of zooplankton. So at the time I am more or less familiar with those stuff, and the main goals for my next 4 years work will be one, to broaden the knowledge about the taxonomical composition of the seasonal and interannual variability of the meroplankton, not only in Isfjorden, but also have a wider perspective of their spatial variability, taking into account some other regions of the Arctic, like Greenland Sea or Norway Sea. And the second one will be the using both morphological and genetic methods in marking the meroplankton from the samples to have a better resolution of their taxonomical composition. And at the end, I am really glad to be a part of this community of this doctoral school. And I think the few next years will be full of new challenges and new friendships and full of memories for years to come. So I really thank you for that opportunity.
Thank you very much, Veronica. Then I would like to ask Mohit Pulara to introduce yourself.
Good afternoon, everyone. It's my pleasure to present myself. I am Mohit Pulara and I am from India. I have done my master's in geology background, and after that I pursued a postgraduate diploma in mountain ecosystem and climate change. In the last few years, I have worked for a huge nationalized project of National Mission on Himalayan Studies, in which I worked for Indian Himalayan tree-line species, and I generated a long climatic reconstruction for tree-line species there. At present, I'm working as a research scholar under International Environmental Doctoral School at University of Silesia. under the supervision of Professor Dr. Magdalena Opala from Faculty of Natural Sciences. And my PhD topic is dendroclimatic response of tundra vegetation to contemporary environmental changes in Arctic region. In this, I'm much excited because as I have in past, I have done for the Himalayan species, and now I will get the opportunity to work on Arctic and to work on the shrub species. All things will be very new, and I will going to learn the wood anatomical part also. So in this, I'm going to gather a vast knowledge about the Arctic greening by understanding the growth pattern of Arctic shrubs. As we know that the shrub expansion is increasingly observed in the Arctic and subarctic environment. So this study of dendrochronology in Arctic region will be very helpful to provide a broader climatic reconstruction of the pre-instrumental period of the Arctic region. And yes, I'm very excited to be the part of the University of Silesia and to work under Professor Magdalena, as much as I have been in contact with her through mails. So I found that she is very supportive, and she is very good in providing her guidance. And she is also very supportive as from the starting month, she used to telling me about how to apply for the grants and how to apply for the different workshops, international workshops of related to this work. So yes, that's all. Thank you so much for this opportunity.
Thank you, Mohit. Then Marcin Mieszczak, please, it's your turn.
Hello, everyone. Thank you for having me here. My name is Marcin Mieszczak and I'm Polish. I graduated petroleum geology at AGH University of Science and Technology in Krakow. My geological experiences so far are related to sedimentology, having a chance to take part in projects related to geology of Botswana, Poland, and Spain. During my PhD project, I changed the discipline for geochemistry. The title of my PhD project is Tracing Archean Crust in the North Atlantic Craton of Southwest Greenland, and it's led by Professor Monika Kusiak. This project is related to the early Earth, the very first billion years of history of our planet, which remains mysterious and unknown yet. There are only 12 regions around all the Earth where these old rocks occur, and one of them is North Atlantic Craton. This area is not well known yet and surveys are scarce. So the target of my PhD is to obtain more data about the geology of the region. This will allow us better understanding of continental growth. My observation will be compared and correlated to the observation of Tan Mai, who will present itself after me. That is gonna build a linkage between Southwest Greenland and his zone of focus, North Labrador. The method I'm gonna use is uranium-lead dating. I will focus on crystals of zircon and date rings of growth of mineral, which are for geologists a time capsule. And measurements within one crystal will indicate the history of changes of geological settings. It will enable me to interpret the geology of the zone, and comparing geological settings of two zones will lead to find missing linkage between two regions, Southwest Greenland and North Labrador. Thank you.
Thank you, Marcin. So it's time to give the floor to Tanmay Kaluskar.
Good morning, everyone. It's my pleasure to be with you here. I am Tanmay Tushar Kaluskar from India. I did my master's from Indian Institute of Technology, Bombay. My master's thesis was based on physical volcanology of ignimbrites associated with Deccan traps under the guidance of Dr. Hetu Sheth. I worked as a research intern at University of Tokyo in volcanology with Professor Mayano Fukashi. In International Environmental Doctoral School, I will be working at Institute of Geophysics, Polish Academy of Science. My PhD supervisor is Dr. Monica Kuziak, Associated Professor at IGF, and my PhD topic is tracing Archean crust in the Northern Atlantic Craton of Northern Labrador. As a team, we will try to understand the early Earth conditions with focus on North Atlantic Craton, which is exposed at southwestern Greenland as well as in Northern Labrador. Our main objective is to study the geochemical signatures of rocks and geochronological study of the study area to better understand the evolution of the Craton. We are going to focus on uranium-led geochronology to reveal the new information regarding the Earth's earlier history and evolution of continental crust at early Earth time period. My work and Mr. Marcin's work, we are going to who is working on southwestern Greenland, are going to compare our observation to correlate history of these two parts at earlier Earth history. I'm very happy to be a student of such a prestigious institute. Thank you.
Thank you, Tanmay. Then I would like to ask Dagmara Litwicka to introduce yourself.
Good morning, everyone. My name is Dagmara Litwicka. 3 years ago, I graduated University of Gdańsk, where I was studying oceanography on specialization marine physics. During my bachelor and my master thesis, I was interested in ocean optics. Then I was working at the GIS Center, also at the University of Gdańsk, where I was teaching GISs and I did some scientific research. And also I was responsible for some administrative tasks. Now I am first year student at the International Environmental Doctoral School. My supervisors are Professor Woźniak from Institute of Oceanology, Polish Academy of Sciences, and Professor Stramski from Scripps Institute of Oceanography, University of California. And during my PhD project, I am going to investigate variability of inherent optical properties in relation to the concentration, composition, and size distribution of suspended particulate matter. And my area of interest will be western part of Spitsbergen. And at the end, I want to thank you for the opportunity for being here with you today. Thank you.
Thank you, Dagmara. Then Sayed Reza Sagravani, please, it's your turn.
Thank you. Hi everyone, my name is Sayed Sagravani, originally from Iran. I studied environmental engineering at the University of Putra, Malaysia, and now admitted into International Environmental Doctoral School at University of Malaysia. My supervisor at the Institute of Oceanology is Dr. Beata Sincha, Department of Marine Chemistry and Biochemistry. My project is Arctic SGD and submarine groundwater discharge in charging Arctic region scale and biochemical impact. Actually, I have two co-supervisors, Prof. Ivo Lepland from Geological Survey of Norway and Dr. Veili from Department of Geological Science, Stockholm University. My project, including 4 objectives for determining the factor controlling submarine groundwater discharge, and then the construction of a history of SGD and quantify the flux of groundwater and investigate the impact of SGD on benefit. We have 4 hypotheses and maybe 4 summary, and for completing this task, we have a few working package. I hope I can I have a good result from this project. Thank you.
Thank you very much. And let's try again to connect with Kayode Adebasin. Could you introduce yourself?
I'm Kayode Adebasin.
Unfortunately, we have a technical problem. Okay, so let's.
I'm a chemist. I studied pure and applied chemistry in my BSc studies.
Unfortunately, due to technical problem, we have to skip the introduction by Kayode. I would like to thank doctoral students for their self-presentation. I'm very pleased to welcome you to the International Environmental Doctoral School community. I'm convinced that the meeting with science that started today will have its continuation, and that it will end with your future scientific discoveries. I wish you persistence in your efforts to understand the complex environmental mechanisms, relationships, and feedbacks, as well as satisfaction with the results obtained. Welcome on board. Okay, so now is the time for the most anticipated moment of this ceremony. The inaugural lecture is always the highlight of academic year inauguration. Today, we are honored to host Professor Jan Pawłowski from Department of Genetics and Evolution, University of Geneva, and Institute of Oceanology, Polish Academy of Sciences. Professor Pawłowski is an outstanding expert in the field of molecular evolution and systematics, and applies molecular methods to analyze paleo and contemporary environmental changes. Under the supervision of Professor Pawłowski, a number of key research projects financed by various European funds were carried out, including the latest one titled Sedimentary Ancient DNA, a new proxy to investigate the impact of environmental change on past and present biodiversity in Nordic seas within Polish-Norwegian research funds. He has published over 160 scientific papers that are widely referenced with more than 20,000 citations. Professor is recognized academic teacher in systematics and biodiversity, evolution, microbiology, marine biology, and supervisor of 12 PhD students. Professor Pawłowski is a member of boards of international societies and editor of reputable scientific journals like Marine Micropaleontology or BMC Biology. The title of today's lecture is Environmental DNA, Looking for Whales in a Drop of Water. Professor Pawłowski, the floor is yours.
Okay. Thank you very much for invitation. I will try to share my screen with a minute. So we will see. Okay, can you hear me?
Yes.
Yes, we can.
Yes. Okay. So thank you very much for the kind invitation and very laudatory, presentation. I don't think I did so much. Huh? I don't know whether you. I will try to show you what we have done in my lab for the last 10 years, and try to somehow introduce you in a quite new domain of biology applied to environmental science. I understood from your presentation that many of you, or most of you, are more oriented toward geology or geophysical sciences. So we will have we'll have to update and go to biology, pure biology. And only at the end, we will finish with some kind of more geological part. What is interesting, I think, about this field of what we can call the environmental DNA is that it covers, in the same time, a large number of domains, starting from the molecular biology, of course, per se, because it's about DNA, but it's also about bioinformatics, about ecology, about environmental sciences, and this is what I would like to show you today, is what kind of things we can do with this new tool. Of course, we will not see the whales in a drop of water, but it's coming to the quite well documented evidence that if you go to the water body, whatever it is, lake or river, you take 1 liter of water, and with this 1 liter of water, I can tell you all fish that live in this water. It was very surprising, and a lot of people did not really believe it, how it's possible that just by filtering 1 liter, you can tell everything what is living there, not only fish, but also birds, insects, and newts, or whatever other animals are living there. This is possible because most of these large-size animals shed enormous amount of DNA into the water. This DNA comes from the skin, it's come from the feces, it's come from excretion, dejection, and any kind of organic material. But in the same time, this water contains huge amount of bacteria, viruses, and other microorganisms. So it's a kind of, what you have here is a kind of mixture. And this is the most fantastic opportunity to really see the entire biodiversity in its global kind of interaction. So, of course, it's applied to water, but it's not only applied to water. Here is just one of the papers that we have just published this month about the different possibility to look for this environmental DNA. It's of course from the water, but it's also from the surface of the sediments, from the sediments itself, or even from soil. It can be, there's a lot of terrestrial environmental DNA also. And what is not included here, but it's also, you can have environmental DNA from air. As you know now, it's a lot of viruses, bacteria in the air, and you can also have a very nice overview of what's happened just by filtering air. And the problem that many people somehow consider as environmental DNA only the DNA from this macrovertebrates, so these large animals, which are of course important. This is what we see, that most of people study, but in fact, we can obtain environmental DNA from any kind of organisms living there. And this comes from, I try to figure out how I can get this, these two. I think, can you see all the screen on this? Is it? Okay.
Yes.
Yeah, because I can't see everything. I try to, yeah. Anyway, okay. So here, what you see that there are different type of support from where this DNA can come, but it also depends what kind of group you are interested in. So this is like a double way to obtain this DNA, this unedited DNA, and it's quite important to know what when you talk about this subject, to know what you are really doing. Where does the DNA come from, but also what you are looking for. And this is what we call here taxonomic aspects that come from this procedure that's called PCR amplification, and that it target the group of organisms that you are looking for. And then you can look from bacteria to vertebrates, any kind of organism possible to target. So somehow it's as I said at the beginning, it gives you the complete overview of what is living in the environment. There are several potential applications if we come to the water, mainly the three applications that are here. Species detection, so we can detect the species, different single species, by using the DNA. This is not something totally new because there was a lot of work done on the detection of pathogens or parasites, and we are all aware about how to detect viruses now. So it's something that is target in a species. But what we will talk mainly here is about the diversity survey. So when we can have a look of all the community, and this is what is here. So it's not only one species, but it's on multi-species. And also even further, we can go further to use this data to some kind of environmental impact assessment or bioassessment, where we can infer the indices or ecological status of the environment just by looking on the DNA. So this is a fantastic way to obtain the view of what's happened in the environment just by looking on DNA of this. And at the end, I will finish also by talking about what have been said already about the paleogenomics. So some kind of overview of how it can be used also for the ancient DNA, ancient reconstructions. So first of all, single species detection. This is the first kind of the most commonly used application of unedited DNA, and this is the example of like a textbook example when you look about single species detection about the fish. This is what most of people think about is this famous invasive Asian carp case study from the United States, where the Asian carp come from Mississippi and migrate towards the north, towards the Great Lakes, and during several years there was a lot of enthusiasm about using DNA to trace the migration of fish across the country. It was a lot of nice, interesting study coming out of it. There was also a lot of doubts about what this DNA really doing and how it's behaving. And this is also very kind of important study to understand that DNA somehow behave a little bit independent from the animal. So you can see you can trace the animal, but until you see the animal, DNA may not exactly show you where the animal is, especially in the case of these big animals like fish. And now today, this study was from 2012, but today we know that DNA can be transported by rivers. And in fact, it's very easy that you can see the DNA even several tens of kilometers out of the place where the specimen lives, which means there's a huge migration of DNA without even migration of species. So there's a lot of problems that are kind of caused by this inherent characteristic of environmental DNA. And this is one of the examples applied to invasive species. There are also another example of using eDNA to tracing the endangered species. And this is where we come to these whales. This is one of these Yangtze finless porpoise, a species of kind of whale that is the extremely endangered, living in China. And there's a lot of studies now trying to figure out where the species is, because it's not always obvious, it's not always easy to spot it. So this study was done by, just published, and was done by Chinese researcher. And it showed quite interesting thing that you not only have to know that you can detect the species, but you also have to see what kind of season you have to choose and where to see. So here you see the difference appears, different quantity of DNA concentration, depending where you look, whether you go on the bottom or middle or top water. So it's all about the water sample, but it depends where the water sample should be taken, and also about the season. It's quite interesting to find that the most of DNA, in fact, is a deeper part of the water, not on the surface or in the middle. And this may come because the whales is foraging, eating on the bottom of the river, or mainly because also because the DNA on the surface is much more degraded. So this is kind of problem that we face, that how the DNA behave in the water. It can be destroyed by UV radiation, by temperature, by acidic conditions, and many others. So all these factors can influence how the DNA is treated. Both the studies, so carp or whale studies, are mainly done by what we called quantitative PCR or RT-PCR, that you know, because now it's used for, if you get tested for your COVID, this is what you use, just to detect single species. But many of eDNA detections are in fact done on the community, on the biodiversity. So in this case, you don't care about one single species. You don't want to know about one species. You want to know about the totality of a group of species, some kind of community approach. And this is done by something that is called eDNA metabarcoding. Why it's possible to do? So it's quite, this workflow show you, it's quite straightforward. You have to take sample, water, sediment, whatever, do the DNA extraction, and do the PCR amplification. This is a very important step, because the step is allowed you to target what you're looking for. But in this particular case, when you do metabarcoding, you don't target single species, you target the community. And then the most important thing is high throughput sequencing, what is called sometimes next generation sequencing. Why high throughput sequencing is important? This, until here, it was possible to do this type of study until 2010 without any problem. But the issue was that there was a little information coming out of this by cloning or other methods. Now with high throughput sequences, you can obtain millions of sequences. So this completely changed. This is a real game changer in all studies of biodiversity, that now we can obtain the millions of sequences. Of course, it's come with a problem, because you have to kind of analyze them. And this is where this dry lab bioinformatics come up. It's this extremely important part, because you have to come from this million of sequences to, for example, ecological assessment or community kind of species table or whatever you are looking for. So there are like two different steps: wet lab, which is relatively straightforward, and dry lab, which is bioinformatics, which is much more difficult. So I'll give you a few examples of how this eDNA metabarcoding can work. But first of all, let's look at this. What you see here, the small points, each of the small points is a sequence obtained by, in this case, Illumina high throughput sequencing. So you obtain billions, millions of sequences in a single run. In a night, you can get up to several hundred millions of sequences. Each of the sequence in the biodiversity study, each of these points will correspond to the species. So you understand now that you have an enormous possibility to explore the diversity, but you also, of course, face a lot of problems how to analyze these millions of points. And I would like to show you a few examples what has been done just by analyzing this huge amount of big data. So one of the best example, I think, is this. We come to the marine environment. I'm mainly marine biologist, so we'll stay with the marine environment. And this is the expedition, French expedition, that explore plankton, oceanic plankton all over the world. They make, during 3-4 years, they make the expedition go and take plankton every places all over the world, trying to get out the idea how much of species are living in the plankton. They take DNA, they take RNA, they take samples for morphology, and the results was quite interesting. That in fact they were published in 2015 in a science paper, and we come to the, it's important to see this curve here, because this curve gives you some kind of, it's called saturation curve. It gives you the idea how far you are in your knowledge. So if the curve comes to the plateau, it means that you know more or less everything. And even if you bring new samples, there will not necessarily be new species. So after analysis of 776 million, so almost 1 billion of sequences, they find out that it's more about something like 150 species. This is it's like a genetic species, of which about 40% are new to science. So that's, for the first time, you could obtain this global vision of what's happened in the plankton. It's not so many species. Some people thought that there would be much, much more, but this is only eukaryotes. It doesn't include bacteria, or viruses. We know that viruses are very, very abundant in the ocean. There's also interesting that it gives you some ideas about the groups that exist in this plankton. And it's not only about big zooplankton or diatoms or algae, but there's also this group that is here, like in violet color, which is what they call heterotrophic protists. Very little is known about these heterotrophic organisms that live there, that feed on the phototrophs, but they're not really very easily and commonly studied. And they depends, of course, to the fraction that is studied. And also something that is very, very interesting, in my opinion, is that the studies show not only what is visible outside, but also what's happened inside the organism. Here you see, this is the diatoms, another protist, several species of protists, and here you see that these protists include inside the phototrophic algae or some kind of endosymbionts. So endosymbionts, this is all endosymbionts living inside the organism. And this is a huge advantage. When you use eDNA, you can really access this endosymbionts. So you can access not only what is visible, but also what is invisible. And here, for example, not only in this endosymbionts are important, but also what is living inside the organism as a parasite, or, for example, pathogens, or in the gut. Everybody of you knows about gut microbiome, but this gut microbiome not only refers to us, but also refers to, for example, zooplankton, like these copepods. You can also see that some organisms, this is a single cell organism that is in fact parasitic, but another organism of the same phyla. Each of these blue things is in a parasite. So this is how this huge biodiversity is generated. It's generated by interaction within the organism. And this cannot be really easily spotted just by, you can do it on few organisms like that. But unvirtual DNA allowed you to have a look at this from much easier way to do. Another thing, and here we come to our whales, is that you can do community network. So not only you see what is inside, what's happened inside the organism, you can see what are the interaction between organisms in the, for example, marine environment. And this was just published in Nature this year, where the people take the environmental DNA and look all domains of life, from bacteria to whales, and give us the possibility to really interconnect the organisms. See how the increase of abundance of one group can have impact on another group. And you see here the seasonality is obvious just by looking. This is bacteria, these are the invertebrates, these are whales. So this kind of network analysis are another way to see what we can obtain from eDNA data. In the second part, I would like also to talk to something that personally we're involved for the last few years. This is more about environmental DNA as a tool for environmental assessment. So we all know, and this has been already said in talks before, about this impact, anthropogenic impacts on the environment. And until now, this anthropogenic impact mainly are analyzed by physical chemical parameters or by different kinds of bioindicators. Now we have a new tool, and this is environmental DNA. And this is what I will show you, how this environmental DNA can teach us about the ecological status and what the changes are. This is how it is now. In most of the cases, when you have to assess the environmental impact, you have to take the samples. In this case, is aquaculture impact. You have to take the samples of sediment, you sieve the samples, you look the animals living there, and you have to identify. To do all this, it's a lot of time, and most of all, you need to be experts. You need to identify the animals, which is, of course, not very common. So this requires a lot of time, a lot of money, and a lot of expertise. And this is probably how it will look in few years. Maybe not immediately, but in few years, you just take a small sample, you go to the lab, you analyze the DNA from the samples, you analyze the sequences that come from your that are generated by your sequencing machine. Of course, you cannot do macrofauna. It's difficult to do these large animals. It's much easier to do microfauna or meiofauna. So this is probably the future of bioengineering, which I believe it is. And in several studies, we have been trying to understand how to connect this metabolic coding to this morphotaxonomy. And for this, we always work on the samples that were done in the classical way and the samples that were done on the DNA, just by microscopy and by high-throughput sequencing. And we compare the sequences. And this is very interesting that, in fact, when you look here, this is a case of salmon farms in Scotland. And when this in the middle is what you obtain when you do morphology, when you do this classical type of assessment of environment. You see immediately when you do this, you see immediately where the impact of organic enrichment that come from the farm ended here, somewhere here. You see the diversity change totally. When you look here, until 60 meters, it's very much impacted and then became much less impacted. What is really interesting, that you can do the same on DNA or environmental RNA, which is even more better, and you obtain the same type of images. So you have a proxy, you have a new proxy that allowed you to obtain the same thing much easier and much faster. And you also see here it's mainly the same opportunistic species, and here it's much more diverse. Much more diverse assemblage. So this is done. This is already proved. There's no question about the possibility to do like that. The only problem is that this can be done like that, mainly for the species for which you know what is the ecology. Because you need the ecology, you need to identify species to know what kind of ecology they represent. And unfortunately, for most of the sequences, you don't know the ecology. And here we go further and we say, if you don't know the ecology, if you know nothing about the sequences, how you would assess the environment in this case. And we find out that in fact you can use artificial intelligence, machine learning algorithms, trying to fit what we know about the ecology of this big species to what we don't know about the ecology of DNA. And we published several papers showing how you can use this information to train the algorithms to analyze the information that come from these millions of sequences. At the end, if you bring the new data, if you bring the new sample, you will be able to use this machine learning and this algorithm to assess this from this new data to assess the ecological status of the environment. Personally, I think this is the future. This is the future of all this bioassessment study. Instead of going to the particular species and trying to find out how it behaves depending on the environment, we can take the huge total biodiversity and using eDNA, using high-throughput sequencing and machine learning, we can decide what is the impact, what is the status of the water body or soil or sediment. But there's a paper in Trends in Microbiology, if you are interested, how to can connect these two different fields and how you can obtain and use it in routine biomonitoring. I almost finished. At the end, this was already mentioned. There is a project that, as I'm now some kind of moving to Poland and will work in the Institute of Oceanology in Sopot, we obtained the new project that is Polish, Norwegian, Greek project on the sedimentary ancient DNA. In fact, it's very similar to what I have shown you, and I would like to use the same type of tools, but apply to history of life, to reconstructing the life in the sediment, not in the water, but taking this course that are here by Joanna Pawlowska from Japan, and just looking on the DNA that is preserved in the course, we can compare different diversity patterns at the different periods. And this is what we'll do in this project, just by analyzing what's happened in mid-Holocene, little ice, recent warmings, and see whether we can kind of learn from the past to see what will happen if, for example, the global climate warming continues. So this is one of the, and on this project that we are just about starting to prepare. And there's also projects that we already done. And this is another project with my Polish collaborators from University of Akademickiego in Poznań. And this is about totally different, it's about tsunami. So you can imagine how many different things. I show you only to give you some kind of scope of the use of this tool. You can do everything. You can, for example, tell when tsunami was there, even without seeing any obvious sign of the tsunami. Only because you will look on the DNA, what DNA of marine organisms are present in the sediment, here in the sediment in Japan, in sediment that are far from the coast, and you just, by looking where this sediment contains the DNA from marine, you can go down to the history and evaluate, distinguish or define the past tsunami deposits. So there's huge amount of possible implication. If you're interested, you have a book. It's called Untitled DNA for Biodiversity Research. It's very good. And it shows why eDNA is so important. First of all, it's non-invasive. You don't have to catch the fish. You don't have to do electrofishing or whatsoever. You just take the water and see what is there. It's allowed you to see unseen, to see the things that you cannot really detect just by microscopy. It persists over time, so it's allowed you to see events historical events that happened somewhere in the time. And of course, it's allowed global monitoring. So everything, the impact can be considered in the totality, not only by one or two species. And this I think that's all. Thank you for your attention. And if you are interested, there's a GNAnet cost action in European that somehow give you all this information and you can join it. Thank you.
Thank you very much, Professor Pawłowski, for an exciting inaugural lecture. I hope that the scientific excellence shown in this presentation will inspire not only PhD students, but all of us. Thank you once again.
You're welcome. Very nice. Thank you.
And approaching to the final part of the ceremony, I would like to thank those who supported the International Environmental Doctoral School in its first year of operation. First of all, I would like to thank His Magnificence Rector of the University of Silesia and authorities of the university for great support and understanding and for creating favorable conditions for functioning of the International Environmental Doctoral School. Similarly, I would like to express my gratitude to the authorities of the partner units of the school, the Institute of Oceanology, Polish Academy of Sciences, the Institute of Geophysics, Polish Academy of Sciences, as well as the Institute of Mathematics, Polish Academy of Sciences, and also Faculty of Natural Sciences and the Faculty of Science and Technology of the University of Silesia. Your favor significantly contributed to the development of the doctoral school in the last year of the last academic year. I'm grateful to supervisors for their involvement in the implementation of doctoral projects, patience, cooperation, and mentoring, allowing development of new generation of researchers. I also appreciate the work of lecturers and instructors, despite a very uncertain situation regarding the epidemic, were flexible and innovative in terms of efficient didactic methods. I'd like to thank everyone who kindly supported doctoral school in its daily functioning, in particular the head of the Center for Polar Studies, Professor Jacek Jania, and the CSP office, the secretary of the International Environmental Doctoral School, members of the admission committee, administration of the University of Silesia, and partner entities. Finally, I would like to congratulate second year doctoral students on the outstanding scientific and publishing successes of the last academic year, and to the newly admitted PhD students and their choice on path to science. I wish you all further successes and implementation of doctoral projects and excellent scientific achievements. So now is a time for final words today. Inauguration ceremony of academic year 2020-2021 in the International Environmental Doctoral School associated with the Center for Polar Studies at the University of Silesia in Katowice is now closed. Thank you very much.
Thank you and good luck.